Hi, in this video we're going to look at PD control design. In the previous two videos we've looked at the the PI controller design and its passive counterpart, the lag compensator, which were used to deal with steady state error, either to make it become zero or to reduce it. So now we're going to look at how we can uh, train the transient response of a system. In this case, we're going to use a differentiator. Remember, in the case of steady state error, we use an integrator. Now, in this case, when we're going to design uh, the PI controller, which is going to be pure differentiator, we're going to be dealing with the transient response. Okay, so with ideal derivative compensation, a few differentiators added forward path of a feedback control system. Remember, when we were dealing with a PI controller, it was we actually added a pole at the origin. And in this case, we're going to actually add a differentiator, and the differentiator basically would be zero. Okay, when we talk of a PI control design, we talk of a pole at the origin. Now we're going to add a zero. It won't be at the origin actually, as we're going to see when we're going to design the PD control. So like we have commented before, if you were designing, if you wanted to modify the transient response of your system and the new port you want to put it at is achievable by gain adjustment, then you would not actually need to design a controller. But in case the port you want to put it at is not on the root locus, then it is then that you would need to design a controller. Yeah. Okay. So we know when we actually differentiate a signal, if you have differentiation is basically a differentiating with respect to time here. So if you have a very small change in the amplitude of a signal over a small amount of time, even if that change is quite small, if it occurs over a small period of time, that can be amplified by differentiation. So we have to be careful when we are using pure differentiation. When you're designing the PD controller, it can lead to noisy, it can introduce noises in our process. Okay, so to tackle sort of this issue with the differentiation and noise, we can of course opt for a passive network. Remember, when we're designing a PI controller, we consider the lag compensator as a passive option for dealing with steady state error. Now, when we're dealing with a transient response, again, we'll have a passive counterpart, if you want, the PD controller, which we're going to call a lead controller. Now, again, it's to do with the phase response. So why we call it the lead controller here? So in this case, the phase contribution of your controller is going to be positive. So we're going to call it as a lead compensator. Before we come to lead compensator, we're going to first discuss the ideal derivative compensator, which is going to be PD controller. So the P again stands for your proportional part, and the D is the derivative part. Now we've seen in earlier chapters, if you're choosing a given point on your root locus, of course, on the left half plane, because you would want to have stability. So the point you choose in the complex plane is going to lead to a peak time and a settling time, because here we're dealing with a transient response of a system. So we're going to deal with the initial response of a system. So the specifications we'll be using to design your controller are going to be things like the settling time, peak time, overshoot, natural frequency. So these are actually your specifications for the transient response. The specifications we've used for your steady state control was in terms of steady state error or your static error constants. But now we're going to use the specifications related to transient. So like I've said earlier at the start of video, if the point is already in the root locus, so you can simply go to that point or select that point by simply adjusting your gain. So then in that case, you would not need to go for control design. But if the pole is not on the root locus, then the root locus needs to be reshaped so that your root locus is going for that point, and then you select the gain to actually be at that point. That's what we're going to look at in this chapter. So one way to speed up the original system, to speed up in terms of transient here, maybe your system is taking too much time to settle, or is taking too much time to peak. So you could actually change these transient specifications by operating at a new operating point. So basically your PD control is going to be something like this. We're introducing a zero somewhere on your real axis. So you would want to choose that compensator in a way, that position of that zero in a given way, so that you obtain your desired transient response. So let's consider an example to illustrate how this design is done. So let's take a system like this, k over s plus 1 times s plus 2 times s plus 5. So you can see here you don't have any finite open loop 0, but you have 3 finite open loop poles at -1, -2, -5. So if we sketch a root locus, we're going to get something like this. So you have poles at -1, -2, and -5. If you apply the rules we've seen earlier, it means you would have a breakaway point at this here between these two poles here, and this one is going to go to infinity. So you have breakaway point here, and you can see this is going to be a dominant poles, but these poles here on the left hand side, the further this is to the left, the more your second order approximation is going to be better. Okay, so let's say in this case here, since we're dealing with transient, let's say we want to operate along this damping ratio line here, which we have put as 0.4. We know that this damping ratio is going to lead to percentage overshoot. We've seen that earlier. So if you draw your damping ratio line and then you find the intersection of these 2 points, we've seen that how to do that in software, but you could also do it iteratively by calculations. I can software again by hand, but by hand is quite complex to do. So we've seen earlier how we find this point here using MATLAB Octave or software or any program you've written. In this case, let's say we've sketched a root locus and then you've drawn your damping ratio line, you found the point. So at the gain case go to 23.72, you're getting this particular operating point, which is your real part here and your imaginary part. Now, bringing this further, we know when you have this complex force at which you're operating, so this value of -0.939 is going to lead to a settling time. So it's going to be 4 over 0.939 is going to be your current settling time. If you take pi divided by 2.151, you're going to get your peak time. Okay. Now, what if you're not happy with the values you get? So you can just quickly calculate your settling time and your peak time. So what if you're not satisfied with these values? Then you would want to move to another point which may not be on the root locus. This is what we're going to see later. Now, since we know we're going to add a pure differentiator in your as part of your control design, so let's just investigate what's the effect of adding pure differentiation in the forward transfer function. So if we just do that for different poles we're adding different zeros, so at -2, -3, -4. So basically here your control is s+2 here, this one is s+3 and s+4. Okay. So if you do that, you can see this was your original root locus here and your intersection which we got earlier. Like we said earlier, keep in mind that this real value here is going to lead to a settling time which is 4 over this value, and this complex part here, the imaginary part, is going to lead to a peak time which is pi over this value. So if you now add a compensator pole at s equal to -2, as you can see here, you've added the compensator pole. Of course, your root locus have changed completely. You can again apply your rules, but you can see here when you add this 0 here at -2, actually you're cancelling the pole, so there's nothing here. There's a 0 pole cancellation here, and your root locus is simply you have 2 branches now. So if you now draw again your damping ratio on at 0.4, now it's crossing at this point here, which is -3 plus j 6.874 at a gain k of 51.25. Okay. So if you compare these two now, so if you calculate the settling time, here's 4 over 0.939, here it is 4 over 3. So you should be able to do a quantitative, but also you can do a quantitative assessment of how your peak time and settling time is changing. So similarly here, if you look at your peak time is pi over 6.874, before it was pi over 2.151. If you were to add now a 0, if you were to add now a 0 at -3, so you can see here, you have added a 0 at -3 here. So your root locus again is going to change drastically. Now you can see here, these two poles would have a branch here. So one is going, one path is going to infinity, another one going to infinity. And then you can see now this branch here for this pole, which would go to infinity. This path before here, but now it's just going to that 0 and that's it. Okay. Now again, in this case here, we are more interested in the dominant pole. So we'll have a pole along this branch here, of course, but we're going to look here because this is what's caused a transient. We know it's when your poles have an imaginary part. This is where we get your transient response. This is where we get oscillation and specifications like peak time, settling time, or overshoot. So we see now when we have this 0 at -3 here is intersecting at this point. So we get a new operating point with a new real part and new imaginary part. Okay. Now this one is an uncompensated one, and now it's a compensator at a 0 at -4 now, and you can see again we get a new operating point. What we're trying to illustrate here is as we add this 0 at different positions, we are adding this 0 as part of your PD control design. So we're getting different operating points. This is what we want to stress here. For each compensated case, the dominant second order poles are further out along the 0.4 damping ratio line than the uncompensated system. So it was here before you had any 0, before doing any compensation. Now, when you start adding zeros, this point is simply moving up along the damping ratio line. And this would automatically mean your settling time is going to reduce and your peak time as well. Okay, so each of the compensated cases has dominant poles with the same damping ratio. So when your damping ratio relates to percentage overshoot, so you'd expect this to be more or less the same. There can be slight changes, we've seen that, and you have to cross-check that by doing simulation, but you expect your percentage overshoot to be more or less the same if your second order approximation is valid. Okay. And also the compensated dominant closed loop poles have larger negative paths, like you've seen, it's moving up on damping ratio lines, so you expect your settling time and your peak time to reduce. Yep, so you can see here a summary of what you've just done. So this was your original uncompensated system. Here we've added a 0 at -2, here a 0 at -3, and here is 0 at -4, and we've looked at all these cases. So this were your operating point by finding the cross section between your root locus and your damping ratio line at 0.4. This is what we've got, and from this value here you can work out your settling time. So how we got this value 4.26 is simply 4 over 0.939, and similarly how you get this 1.33 is 4 over 3. Similarly 4 over 2.437 you get the settling time, and similarly 4 over 1.869. So you can see here this was your original settling time. By adding now the 0, you are able to reduce your settling time. Okay, so if you wanted now to also compare the peak time, so again, we take pi divided by this value. So you can, if you compare the imaginary paths of your compensated operating point to your uncompensated case, you can see they are all larger, and this is 2.151, so you expect your peak time also to be reducing. As you can see here, the full table. So you can see your peak time initially was 1.46 before any compensation. Now by adding these zeros here, you can see your peak time are reduced. Peak times are reduced. Okay. Now, if we just make a small comment here about your, you can of course calculate the KP here, your static error constant, which would, you can see clearly here your KP is also increasing, even if you're not tackling your steady state error, because here we're dealing with transient. You can see as part of introducing the zeros at different points, your KP is increasing, and subsequently your steady state error is reducing. But that's not important that it would always reduce. It can also increase. So it's very important for you to cross-check your steady state error as you're doing your transient changes. Remember, when you're doing your PI controller or lag compensator design, even there we had slight changes in your transient. Even if we were not tackling transient, you wanted to maintain transient, but you had slight changes, and you have to cross-check if the changes in the transient are acceptable or not. So similarly here, as you're doing your control design to deal with a transient of a system, the steady state error would also change. So you have to cross-check, is it acceptable? In this case, as you can see, your steady state error is reducing, so you won't have a lot of issue. But if you're increasing, so you would need to make adjustments. Okay, so what you've commented about the steady state error. So these are graphs here showing the transients, how it is changing. So you can see here before we had quite large error. So as a consequence of trying to deal with the transient, your error is also being reduced, as we've seen. But more important for us here is this was an uncompensated system, which was taking quite a lot of time to settle down. So it's a transient part. The peak time was quite high, as well as the settling time. But now by doing compensation, by adding 0 at -2, -3, -4, you're able to speed up your system. So you can see the peak time has significantly been reduced, and also settling time. The system is settling time quicker. So this is what you want to do with control design for PD controller, or like we simulate a lead compensator, is to improve the transient of the system. So the transient will be related to settling time, peak time, or most. So let's take an example and see how we do that field control design. So let's take this example here. We have a system of type 1, okay, in the forward transfer function. So given the system below, design an ideal derivative compensator to yield 16% overshoot. So this 16% overshoot would allow us to set our damping ratio line with a free-fall reduction setting time. So when you look at the question here, all is mentioned here, design an ideal derivative compensator. So in general, you might not be told what type of compensator to design. You might just simply say design a suitable compensator. So in this case here, since we're dealing with the free-fall reduction settling time, you should know this relates a transient part of the transit response of a system. So it has to be either a PD controller or a lead compensator. The first step you're going to do now, you're going to sketch your root locus. If you just go back one slide, you've seen you have don't have any zeros, any finite zeros. We have finite poles at 0, -4, -6. So you're going to first put your finite poles, and then from there you're going to sketch your root locus, get your branches right, and you can see here you have one pole, of course, on this path here, which is not going to influence the transient of a system. That's not the dominant poles. The dominant poles are here. So we are also given this 16% overshoot. So you can use the equation e power minus I pi over 1 or square root of 1 minus I squared times 100% should be 16%. So you solve for your damping ratio. You get a value of 0.504. And from there, you can work out the angle here. And of course, normally we measure the angle from the positive axis to that line. But when you calculate cos inverse of this value here, you're going to get this angle. So it means from your root locus, you're able to draw a damping ratio line to achieve this 16% overshoot you wanted, and the intersection is the operating point at which you want to be. So this operating point here, we're getting at a gain of 43.35, okay, and this value have minus 1.205. Actually, if you take 1.205, is what we've done here. You take 4 divided by 1.205, you get 3.320 seconds. So it means our settling time here is expected to be 3.32 seconds. Remember, our question was in terms of settling time here. You might be given a question in terms of peak time as well. Then you're going to use this value here to calculate your peak time and do further calculations. Since the question is framed in terms of settling time here, we are computing settling time of 3.320, and the aim of the problem was to reduce the settling time by 3. So it means your current settling time is 3.320. The new settling time is 3.320 divided by 3. So you want to achieve now a settling time of 1.107 seconds. Okay, now what you can do now is you can simply calculate what real part of that operating point you would need to achieve a settling time of 1.107. Yeah, so the settling time we've got it to be 1.107. It means a new operating point we need to have a real part of minus 3.613 minus, because you will need to be on the left hand side. Now from this real part of your operating point, you can also calculate the imaginary part, because it's in the complex plane. You would have an imaginary part as well, and you can do that by trigonometry. So at this point here, we know our operating point has to be along this damping ratio line before we're somewhere here. Now, because we want to reduce settling time by a factor of 3, so we found that the new operating point would need to have a real part of 3.613. You got that? And since it's along the same damping ratio line, you can now by trigonometry calculate what imaginary part would you need. Very simple trigonometry here, and we get a value of 6.193. It means a new operating point you want to be either minus 3.613 plus or minus J 6.193. Okay, so just seeing a very good summary here showing before we were somewhere here, and at this point here we were getting a settling point, a settling time which we were not happy with. We wanted to move to settling time which is 3 times less, and we've calculated this has to be along the damping ratio line because we want to still maintain the same percentage overshoot, the same damping ratio. That's a very important locus for us here, and by doing some trigonometry, and we've found a new operating point to be at this. Now, next question, like we said at the start here, does this new operating point lie on the root locus? Visually here we see no. Actually, the root locus is going to do something like this here. So definitely the new point we want to operate at would not be on the root locus, but there's a very accurate way to check that is simply by finding the angle. Remember we said all points in the root locus would contribute an angle of plus or minus 180 degrees. So if you want to take this point here and link it to all your poles and zeros, in this case there's no zeros. So if you create vectors here from your finite poles to this point here, okay, and you get all your angles which are created and you sum that, bearing in mind that your poles would have negative angles, this sum should come to plus or minus 180 degrees. So clearly this point here would produce an angle of plus or minus 180 degrees, but this point would not. Okay, so at this point here we see the new operating point at which we want to operate is not on the root locus. So we need now to design a controller to make the root locus go for this point. Okay, so let's see how to do that. So this is what I've just said about the angle contribution being 180 degrees. So what can you do now? You can work out what angle are we getting at this new operating point. Okay, so if we work out the angle at the new operating point, we can deduce how much angle needs to be adjusted to make that operating point become part of the root locus. Okay, so if we were to calculate the angle at this new operating point, we definitely not get plus or minus 180 degrees, but we'll know what angle is missing for us to actually get that sum of angle to be plus or minus 180 degrees. And so the zero we're going to introduce should provide this difference in angle, should provide this adjustment. So as we've done before, let's construct vectors now. So this is our new operating point you want to be at, and these are your three poles. So if you construct vectors from your poles to this point, and then you get three vectors here, then you would need to calculate this angle. So this one we already knew it, it's 120.26 degrees, because this one is already along the damping ratio line itself. Now the two new angles we calculated simply by trigonometry, so tan inverse of 6.193 over 0.387, so that's a small distance here from 4 to 3.613. This angle you get here of 86.42 degrees. The other vector here from the pole at -6, so you get an angle of tan inverse of again 6.193 divided by now the distance from -6 to minus 3.613, so you get a distance of 2.387. Of course, here we are not, these are distances, you're not taking negative signs. So we get an angle of 68.92 degrees. So we take a sum of all these angles now. Since they're all poles, it's going to be just negative signs. So minus 68.92, minus 86.42, minus 120.26. We get an overall angle of minus 275.6 as expected. It is not minus 180 degrees. So therefore, to bring that angle to 180 degrees means we need to add a positive angle of 95.6 degrees. So this is what the zero would provide. The zero we're introducing as part of the PD control design. Remember, the zero is going to control the positive angle. So the angle that zero has to bring is 95.6 degrees. So zero can be added to provide a positive angle, and its position should be set so that the angle of this vector is going to create is going to be 95.6 degrees. So will that zero you're adding be to right or left or minus 3.13? So remember, this is your operating point here. Like the question being asked here, is the zero you're adding going to be on the left-hand side or on the right-hand side? If it was exactly minus 3.1613, the angle contribution would be exactly 90 degrees. Yep, that means it has to be on the right-hand side. Then the angle will be more than 95 degrees. If your angle contribution had to be less than 90 degrees, then you're going to put it on the right, on the left side. It has to be on the right of minus 3.613 to give an angle greater than 90 degrees. So by trigonometry again, you can work out the position exactly, which is actually your PD control. So this is where now we're placing the zero, which is the PD controller. Okay, so it's slightly to the right here in this case, but we don't know where ZC is currently. This is what we have to work out. So again, it's a very simple trigonometry problem now where we know this is minus 3.613 plus J 6.193. So this is the operating point. And then we also know the angle that this zero should provide is 95.6 degrees, because that's what's missing from the sum of angles for this operating point to provide or to lead to an angle of 180 degrees. If the sum of angles to that point becomes 180 degrees, it simply means the locus is going for it. So if you just do a simple trigonometry, I've just drawn a new triangle here for you to sort of see what calculation we're doing. So we have a 95.6 degrees, so you can easily work out this angle here. We have the position of a zero here at minus ZC, so you see what we're trying to find out. We know the operating point is minus 6.613. and we know the height of this the height of this triangle, if you want here, is at definitely 90 degrees. The height is 6.193. So you can just simply calculate the distance here. So tan of this angle here, tan of 180 minus 95.6 degrees is opposite 6.193 over the distance here. So the distance here, again, we're not considering sine here. The distance is simply 3.613 minus ZC. That's the distance that we have here. If you solve for ZC from this equation, we get 3.0036. So ZC here is 3.006. It means the position of 0 you're adding is minus 3.006. Okay. So this is what's shown here. So if you were to add a 0 at this point here, your root locus would now go through this point. Okay, so let's see the summary table now to illustrate your uncompensated system. So this is what we had before. Remember, we calculated the operating point, and from there we calculated the settling time, and we have divided by 3 to get this value here. Now you can see here, this is actually what you expect values to be, and this is what you're getting in simulation. Why this difference here? Simply because this is second order approximation. The system is third order here, and you're approximating that by a second order system. So when you do simulation, you can find it is slightly different. Your overshoot is not 16%, it's actually 14.8. So we expect to have slight differences like we discussed before. So now we've calculated your compensator by adding a 0 at minus 3.006. So if you do that now, this becomes your dominant poles. You expect your settling time to be reduced by 3. It has more or less reduced by 3 actually. So it is not 1.107. By simulation, when you simulate the step response of the system, you're getting 1.2. Okay. And you can find as a result of peak time has also reduced. As expected here, if you find your operating point to be this one here, so you can see your imaginary part has also been increased here. So you expect your peak time to also reduce. So this is our PD controller design with your specifications to do with your settling time, peak time, or any of the transient parameters. You can use them now to calculate a new operating point. From that new operating point, you can find what angle would your PD compensator need to provide, and from there you can just situate or locate your 0. That's more or less what you do in PD control design. So this is your new root locus now. The shape has changed considerably, but importantly here, your root locus is now going through the point you want to be situated at, and from there, of course, you can work out the gain that you need to set on the system. It won't be the same gain as before. So you need to find out the gain at which this point is obtained, and this is what you're going to tune your compensators that you are this gain, and you expect to get a transient point. Okay. So this is your step response here. Before, this was your uncompensated system, so taking quite some time to settle down, and your peak time was also quite high. By doing the compensation, we've designed the controller we've designed with a pole with a 0 at minus 3.006. So you can see here your overshoot is more or less the same because we are operating on the same damping ratio line, but your peak time has reduced and your settling time has reduced as well. Now, this is the general form of a PD controller here, where you have the proportional part here and your derivative part. So this one has a gain associated with it, K1, and the differentiation part as well has a gain. So if you lump these two together here, you're just doing a summation here. So you get the general form here for your PD controller. So by simple comparison, remember we said when we were doing the design, we found the gain to be 47.45, and then the 0 was at 3.006. If you just do a small comparison here, you find that the value that you choose for K1 is actually 142.6, and the value of K2 is actually 47.45. So if you want to represent your PD control in this form here, this would be the values of K1 and K2 you would choose. This is what we've obtained in that table here. If I just go back here, so this is actually your PD controller. Yeah. Okay, so let's discuss now lead compensation. Is very similar to what we've just done, because what we've basically found here is your controller, your compensator need to provide a positive angle contribution to be able to bring your root locus to pass through that point. Now, what we're going to look at here in lead compensation, we won't be adding only 1 0, because when we want to add only 1 0, remember when we're doing a PI controller, when you want to add only one pole at the origin, then you needed active systems which needs power supplies, and then we want for lag compensator. So again, here we see the PD controller is basically only 1 0 along the real axis. So if you try to do that, so the electronic circuitry which we need to do that would consist of active components, which if you want to avoid, and also if you want to avoid the issue of differentiation, you can go for a lead compensation. So lead compensation would not have just 1 0, it would have 1 0 and 1 pole as well. So let's see how this works now. So in this case, we won't be just adding 1 0 here, we'll be adding a 0 and a pole. So these are advantages that we've seen. So basically what we're doing here, if you just forget about this pole here, which we are going to add in lead compensation, what you've just seen, if you add this 0 here in your system, which we did for the PD controller, your angle contribution here written as θ2 is simply allowing this desired operating point to pass the root locus. So basically what you are providing here is a θ2. Yeah, if θ2 is the angle the controller is providing. So now if you were to add, in addition to this 0, you also add a pole as part of controller design. It means now you are also introducing an angle θ2 here. Sorry, θ1. So θ2 is from the 0 and θ1 is from the pole. So the difference of the two, so this is very nicely shown here. So if you use the alternate angles mathematical construction, so this θ2 is the contribution from your 0, so it's a positive angle, and the θ1 is the angle contribution from your pole. So if the difference you find here, which is θ2 minus θ1, so you get angle contribution here for what is written as θc. So that's what your lead compensator, so your lead compensator is giving. So before it was just θ2 with a 1 0 only. Now it's θc, which is θ2 minus θ1. Okay. So this is that component which is being provided by your lead compensator now. Before it would be just θ2. Like you see for the PD controller. Now, clearly here you find that there are many ways you can provide an angle of θ2 minus θ1. Let's say θ2 minus θ1 is 60 degrees. So there's not just one single combination of a 0 and a pole which can give an angle of 60 degrees. You can have many combinations of zeros and poles along your real axis which can give that. So you have a subjectivity here when you design your lead compensator. You would need to set a particular 0 and then find the corresponding pole, and then you will need to do simulation to see what impact has this choice of your 0 and the corresponding pole had on the transient or the steady state error, and if that's not correct, then you need to refine. Let's take an example here to illustrate the design of a lead compensator. Is going to go very similar to what we've done for the PD controller, except now we would of course need to arbitrarily set your 0 somewhere and then find the corresponding pole to get the angle contribution you want, and then from there you will need to do simulations to cross. So you can see here again, that's the way the question is formulated here is design a lead compensator for the following system that will reduce setting time by a factor of 2. So here we want to reduce the setting time by a factor of 2, and we want to maintain a 30% overshoot, means you want to still operate around the same damping ratio lines. So first step, you're going to draw your root locus and then find the point of intersection. So that's what we've got here. And then next step, from this operating point, you would find the settling time. From the settling time, you will halve that. So you've done all the steps for the PD controller. I'm skipping these steps now. So you will halve that. And then when you calculate your new settling time, you would calculate what real part would you need to get this settling time. So we're getting value of 2.014 here. So you cross-check this. And once you've got 2.014, you can use trigonometry here because you want to still operate around the 0.358 damping ratio line, which is giving a 30% overshoot. You would work out the operating point to be minus 2.014 plus J5.252. So this operating point here would give you this damping ratio, which you want at the same time as setting time you want. Of course, this also would reduce your peak time, as I said. Let's bring it from here onwards. So I expect you to be able to find a new operating point from the specification that you want to reduce the settling time by a factor of 2. Okay. Now, just like we've done earlier, so you're going to work out all your angle contribution, and we expect this point not to give an angle contribution of plus or minus 1 degrees because it's not on root locus. So when we do that, we get an angle of minus 233.069 degrees. And of course, this means now if you want to achieve an angle of minus 180 degrees, it means your controller, your compensator needs to get an angle of 53 plus 53.069 degrees. If you were designing a PD controller, you just set 1, 0, which is going to give that angle here. It's going to be now on the left here, as you can see, because angle is less than plus 90 degrees, so it can't be on the right of your operating point, it will be on the left. Okay, but now we look at the lead compensator, means we want to introduce not just 1, 0, but a 0 and a pole, because we want it to be a passive component. Okay, so this is where I would say a bit of subjectivity is introduced here, where you would need to first set a suitable position for your 0, and then calculate the corresponding pole, and then you will need to do a simulation and cross-check, are you getting a suitable response for transient and maybe your error. If your error is increasing too much or you are not getting the proper transient, it simply means here your dominant pole you're getting is not providing a suitable second order approximation, and you would need to choose other places for your zeros. So it's a bit of an iterative process here. So let's first try this 0 at minus 5. Remember, the angle provided by that is to be provided by your compensator. Your lead compensator is 53.069 degrees. So if you were to introduce a 0 at minus 5, let's see what you get. So we have introduced here 0 at minus 5. The angle here is 60.38 degrees. So again, you join that 0 to your operating point, and now angle you get is 60.3 degrees. Just by trigonometry here, you do tan inverse of 5.252 divided by 5 minus 0.014. So this angle you get 60.38 degrees. Now, of course, this is now with zeros. This is one angle contribution here is positive. All your other angles are negative because they correspond to poles. You get an angle of minus 172.69 degrees. Okay, so still you're not at the minus 180 degrees because you've not chosen this position of the 0 at minus 5 to actually get this angle of 53.069 degrees. You arbitrarily put the 0 at minus 5. Now it means the remaining here from minus 172.69 degrees, if you want to go to minus 180 degrees, it means you still need an angle of minus 7.31 degrees. So minus means it corresponds, of course, to a pole. So the pole you're going to add now should give an angle of 7.31 degrees. Quite a low angle. So you can see it's going to go far to the left of your, imagine this angle here becoming 7.31 degrees. It has to be far to the left here. Okay, so again, you can do that at trigonometry. We found the angle to be 7.31 degrees, which the pole needs to provide. This is the pole we need to introduce in addition to that 0 at 5. And by trigonometry now, so tan of this angle here, which we've got to be 7.31 degrees, has got the opposite. So opposite, we know this operating point here is 5.252 divided by the distance side, of course, is the PC here. We put both are negative, so the distance is simply PC minus 2.014. This is what we have here. So if you were to solve for the position of the pole here, we get 40.96. So I expect it quite far to the left. So once you get that, it means your lead compensator is, remember you had 0 at minus 5. Now you're introducing a pole at minus 42.96. So this is your lead compensator. This is the root locus you're going to get. So you introduce that 0 here at minus 5 and a pole at minus 42.96. So you can sketch your root locus again. So you can see here you have this part of the real axis forming part of the root locus and you have breakaway point here. So this is where you will break when you draw the damping ratio line. So this table here is a summary here of what you've done, but also considering other points where you could have put your zeros. We arbitrarily set at minus 5. Remember, but we are just checking here if it was minus 4 and minus 2, what happens. So this is your system without any compensation. Yep. So this is your dominant poles here obtained by intersection of root locus with your damping ratio line at 0.358, as we computed with the 30% overshoot. Okay, and you see your settling time as calculated, and the ones in bracket are the simulated ones, so a bit different because again you have a second order approximation you're trying to do here. So this is what we've done when you actually introduce the 0 at minus 5 and the corresponding pole to obtain the dominant poles which you want. So this is what we've got. So your settling time has reduced more or less by 2. This was our specification. This was our main goal, to reduce it by 2. If you just look at your steady state error, it is reducing. has reduced. If you do that, it's reduced a bit, and your second order approximation is okay because you're more or less getting what you want. It's very close to values. Now, what if you introduce the 0 exactly at -4? So you can see here you have a pole 0 cancellation. Yep. And you would correspondingly find, just like we've done here, where we introduce -5, you got an angle, and then you find what's the location of pole you want to find, what angle. So similarly here, if you introduce a 0 at -4, you can correspondingly calculate what pole you need to add. So in this case, we got a value of -20.09. And in this case, again, you find your settling time is very similar. Okay, your peak time has also reduced, and your second order approximation is okay because the values are okay. Now, in this case here, we are introducing your 0 at -2. So this is still your operating point, and you find your setting time is more or less very similar, but in simulation is actually lower. Yep. And your peak time has also reduced. And then you have a steady state error here, which is, if you look at the steady state error, before it was 0.308, and now it's 0.312. So steady state error has reduced to a lesser extent when you do that, but overall it's fine. So you can see here, by doing compensation using different positions for your zeros, that's fully permissible, but you have to cross-check in simulation, are you getting the transit response you want? But for each 0 you're introducing, of course, the pole that you need to introduce for that lead compensator would be different. So you can just work it out using the method we've done. This is just a depiction here of the different step response you're getting. For all cases, we expect to get the same percentage overshoot. Setting time should be reduced. As you can see here, your uncompensated system here is taking lots of time to settle and your peak time. But for the 3 compensators we've seen in this table here, in all 3 cases, your peak time is actually reducing, your setting time is reducing. But if you look for compensator C here, you find that the overshoot has as well reduced. Yep. So this is something you have to cross-check, most likely because of the other poles that you're introducing. The system is coming closer and closer to the poles that influence the system. Okay, so this is where we stop for the PD control design and the lead compensator design. So till now, just a quick summary. In the previous video, we looked at PI control design, lag compensator. Now in this video, we look at the PD control design to deal with a transient response of a system to improve it. And then we look at the lead compensator as the passive counterpart of your PD controller. Now from here, it means you look at the PI controller and PD controller, the lag compensator, the lead compensator. Now, if you're given a problem now where you want to deal both with your steady state and your transient, then you're going to go for PID controller or a lag lead compensator. This is what I'll be covering in the next video. Thank you very much for watching.